Now we have a solution now, a complicated solution. So, but it may be more instructive if we look at this solution carefully, especially when we are getting close to the resonance. Now this is a square of the amplitude for a false oscillator. Now we want to simplify the math a little bit because actually the message here is quite clumsy, especially the omega dependence. So we want to restrict ourselves. If the damping alpha is small, okay, we restrict ourselves to a small damping in this case. And if alpha is small enough, then this term, the second term in the denominator will be small, okay? And actually, that will affect the result only if my omega is close to omega naught, okay? In the vicinity when omega is close to omega naught, then the second term will be not negligible. So that means we can approximate the omega in the second term by omega naught, because this term will only be important when omega is getting close to omega naught. So we can actually approximate this omega by omega naught. This is the idea. When omega is far from omega naught, the second term is small, okay? So it's not important anyway. And the only regime where the second term will become important is when omega is getting close to omega naught. And in that case, we can simply replace this omega by omega naught. And what will then be the maximum amplitude? The maximum amplitude happens, you can see now, the maximum amplitude happens when this term is 0. Now, this term is always positive or equal to 0, right? Because it is the omega naught square minus omega square square. So this term is always positive or 0. So in order to make the amplitude largest, you have to make the denominator smallest. So that means when omega become omega naught, this time vanish, the amplitude is becoming largest. And so we got the maximum amplitude by setting omega equal to omega, which is just a resonance. Okay, at the resonance, the amplitude is largest, and I call it A maximum. Okay, so without this term, when this term vanish, at omega equal to omega naught, the amplitude square is maximum, and the maximum value is equal to F naught over M square, 1 over alpha square omega naught square. Okay. Now this is still an approximation. This is actually still an approximation. If you look at the original formula, if this is not omega naught but omega, then you will find that the minimum value of this guy of the minimum value of the denominator is not exactly at omega naught, but it's slightly different from omega naught. But the difference is not much. So that's why we make such an approximation. Okay, when omega is close to resonance. Okay. And we are also interested in the width of the curve. Now this is a graph of A squared versus omega. We know the height now. The height is A maximum square, which is this guy, right? But we also want to know the how wide the curve is. That is when omega is far from is different from omega naught. How fast the amplitude will decrease. Okay, so that characterizes the width of the curve characterize how fast the amplitude will decrease when omega is getting far away from the resonance. Now, so this is the formula. This is the general A. A squared is given by this, with the approximation here. Omega, I assume omega equal to omega naught because I'm getting close to the resonance anyway. Now the maximum amplitude is given by this, right? Okay. Now I divide it by half. Why? Because I can define the width of the peak as the like this. This is the maximum. I would divide the maximum by half. Okay, so I got the half maximum. At the position of the half maximum, the width of the curve characterized the width of the peak. Okay, so we are going to find the delta omega here at the position of half maximum. Okay, we want to find when A maximum square is divided by half, the difference between these 2 points, that is the width of the peak. Okay, so that means I can equate A square. I can equate A square with half A maximum square. Okay, I can equate this A square with half of the maximum amplitude square. So now you can see when I make these 2 terms to be equal, the constant f naught over m square cancel, and I have 2 alpha square omega naught square equal to this guy, right? And so one of this will cancel, and I will got this equation. Okay, now this is obtained by putting A square equal to half of A maximum square. Okay, so that is a simple algebra. Now this equation is easy to solve. We can take square root of both sides, but be careful. If we take square root of both sides, we have to include a plus sign and a minus sign. Because even with a minus sign, when we square it, we come up with the original equation. So in order to include the both, this is positive and this is negative, we have to include this sign, this plus or minus sign. And these 2 signs exactly give us 2 solutions corresponding to this point, which is larger than the maximum, and this point, which is smaller than the resonance. Okay, so these 2 points exactly corresponding to the plus sign and the minus sign of this equation. In effect, we are solving a quadratic equation. Okay. Now we make another approximation now. We notice that the left-hand side is omega naught square minus omega square. So it can be factorized as omega naught minus omega multiplied by omega naught plus omega. A square minus B square is A minus B multiplied by A plus B. Now I cannot make omega equal to omega naught in the first term because that will be 0. That would be incorrect. But for omega naught added to omega, because omega is not much different from omega naught now, so I can approximate the second omega as omega naught, and this bracket will become 2 omega naught. What we have done is that I assume the peak is narrow, so I can make this assumption. Okay. Now, if I make this approximation, then omega naught will cancel on both sides, and eventually we have a simple enough equation that allows us to solve for the omega. Okay, we find that omega naught minus omega is plus or minus alpha over 2. So omega is actually omega naught plus alpha over 2 and omega naught minus alpha over 2. So we got 2 solutions, right? The 2 solutions are actually omega equal to omega naught plus alpha over 2 and omega equal to omega naught minus alpha over 2. The first solution is here. And the second solution is corresponding to here. So you immediately realize that the width of the peak that is characterized by the half maximum is alpha. Okay, it's alpha. So delta omega is actually alpha. The difference between the 2 solutions of omega is actually alpha. Now in this graph, we plot the A against omega, but not the A square now anymore. Okay, so this becomes A maximum. And if I take the square root of A maximum square over 2, I got A maximum over square root 2. Okay, I just take the square root of this guy. Now, so I can see interesting features. for this so-called resonant curve, the height of the curve, now the maximum value is corresponding to f naught over m 1 over alpha omega naught. It is actually proportional to 1 over alpha. So the height of the curve is proportional to 1 over alpha. And now we also find the width of the curve is proportional to alpha. Okay, this width is proportional to alpha, while the height is proportional to 1 over alpha, the reciprocal of alpha. Okay, so that means what? And that means if I have my alpha to be small, if I have a small alpha, that's a small damping. The resonance curve with a high peak, the peak will go to a very high value, but it will become very narrow. Okay, because the peak height is inversely proportional to alpha. So if I have a small alpha, then I have a high peak. But the width is proportional to alpha. That means if I have a small alpha, I have a very narrow peak. Okay, so the small damping means a narrow but a very high peak. And on the other hand, if I have a large alpha, which means a large damping, then I have a Y curve, but have a lower peak. Okay, so this is the properties. These are the two curves summarizing the case for large alpha and a small alpha. Okay. Now, physically, what is the meaning? Physically, it means that if the damping is small, then the system is absorbing the energy, is the resonance. So it oscillates to a very high amplitude. But the resonance is actually very sensitive to frequency. If I get slightly off the resonance frequency omega naught, the amplitude will decrease very rapidly. Okay, the amplitude goes to very large value at exactly the resonance frequency. If I go slightly off, then the amplitude will drop very sharply. That is a physical meaning. But if I have a large damping, then that means the system is dissipating a lot of energy. Then the resonant peak will be low, which means that the maximum amplitude is not that high. Okay, because the system dissipates a lot of energy. And this curve is more gentle, which means that if I'm off resonance, the amplitude will not decrease very rapidly. It will not be so sensitive to the resonance phenomena. Okay. But how about the phase? Let's see the phase, right? We have the force given by cosine. The x is given by cosine omega t minus theta, right? And theta, as we have found, is arctangent alpha over omega, alpha omega divided by omega naught squared minus omega squared. Now you can see in this definition, the angle goes from 0 to pi. The range of the angle actually extends from 0 to pi. Pi is half of a wavelength. 0 is in phase. Pi is 180 degree out of phase. And an angle that is larger than this can be, it's just the same as the original range. Now this actually fully describes the phase change. Now let's consider the situation when omega is smaller than omega naught. When omega is smaller than omega naught, then this guy is larger than 0, right? The argument inside the arctangent is larger than 0. And that means the angle theta is more than 90 degrees. Because arctangent, something that is larger than 0, means the angle is smaller than 90 degrees. On the other hand, if omega is larger than omega naught, is larger than the resonance frequency, then this becomes negative. And since we define the range of theta from 0 to pi, then theta will then be larger than pi over 2. Okay, theta will be between pi over 2 and pi. Okay. Now there's a minus sign. This is only a convention. There's a minus sign that goes before the theta in x. Okay, so when the curve f looks like this, if I assume in this figure theta is positive, Then minus theta will corresponding to shifting the curve of x by a quantity in time t in terms of theta as theta over 2 pi t. Okay, now this we have discussed before when we learned about phase. Okay, if I have a negative phase shift, if theta is positive, then with the minus sign I have a negative phase shift, right? And that corresponding to the shifting the curve to the positive t direction, and by this amount. Okay. On the other hand, if I have a negative value for theta, then with this minus sign become positive, and that will strip the curve to the left hand side. Okay. So this is a variation of the angle theta with omega. When omega is smaller than omega naught, then the angle is below pi over 2 or 90 degrees. If omega larger than omega naught, then the angle is between pi over 2 and pi. So these are the summary. Okay, and there are some special case. If omega is very small, then the angle will tend to 0. If omega is very large, then the angles will tend to pi. You can see from this equation. And also, when omega is exactly the resonance, when omega is exactly equal to the resonance frequency, this quantity will become infinite, right? And arctangent infinite will become pi over 2. So the curve will cause us pi over 2 at this point, okay, at the resonance point, okay? So these are the summary for the phase difference between X and F, okay? So we have ended our discussion on oscillation. Now the last part is actually a little bit difficult, okay? So I would be appreciate if you have spent more time in looking at the direction that I discussed with you today. And if you have difficulty in understanding, you are welcome to contact me. And if you are quite confused about the direction, please focus on the application, and also focus on the meaning of those terms in the equation. The direction is actually not very important. If you learn about complex number in your senior year, then you will find that it will be much easier for you to use complex number to solve this problem. But I will not go into the details of using complex number in this course, because it's only introductory course, and not all of you know about complex number. So I better skip that part. Okay, so I use a traditional algebraic method to solve the differential equation, and that would be rather clumsy. Okay, so please ignore the detailed derivation and focus on the application of if you are not able to manage it. Okay. So any question for this part on the chapter of oscillation? Any question? Any more question? If not, then we will start a new chapter, and this is also our last chapter. It's on waves. Okay, we eventually have comes to waves of this course. Now, just like what we did before, we first discussed about the kinematics of waves. We would like to describe the know how to describe a wave using a mathematical expression. Then we proceed to show that the waves actually satisfy Newton's second law. Okay, and that is the dynamic. Okay, first we discuss about the kinematics. We describe the motion by using an equation. Then we will show that equation actually satisfies Newton's second law, and we will describe it using the wave equation. Okay, and that is the dynamic part. Okay. Now there are different types of waves. Waves phenomena are actually very common in physics and very important in physics. Actually, you can't get rid of waves in any branches of physics. Um, and there are typically three main types of waves. The first type of wave is mechanical waves. Mechanical waves is actually governed by Newton's second law, and it only exists in a material medium, such as a solid or a gas. Okay, when you are set up a vibration in a solid or gas, the vibration will propagate inside that medium, and those are the waves. And examples of those waves are the water waves. For example, if you throw a stone on a pond, then you can see on the surface you have surface wave extending outwards. You have ripples extending outwards, and they are surface waves. And you have sound waves. Sound wave is just the longitudinal wave due to the vibration of air molecules. And you also have seismic waves. For example, during a earthquake, there may be a wave propagating along the surface of the earth. Okay, and there are actually at least two kinds of seismic waves. The first kind is called P waves. Now, P wave is just a longitudinal vibration. It's a compression and rarefaction. It's a longitudinal waves. And this is a kind of seismic wave called P waves. And for seismic wave, you also have transverse waves known as S wave. The S wave is a shear waves, which means that the direction of vibration and the direction of propagation, they are mutually perpendicular to each other. Okay. Now there actually are more kinds of waves for seismic wave, but I'm not going into the detail. It's sufficient for you to know that you have longitudinal wave and transverse wave for earthquake. Now we also have the electromagnetic waves. Electromagnetic waves is an oscillation of electric field and magnetic field. When the electric field and magnetic field oscillate, they induce mutually inducing each other. So the changing E field induce a B field, and the changing B field induce a E field, and that result in an oscillation. And that oscillation will propagate in space and also in a material medium. And this is described by the so-called Maxwell equation. Maxwell equation is the equation that summarizes, that describe all the electromagnetic phenomena. Maxwell in the 19th century discovered 4 such equations, which completely described all electromagnetic phenomena, including electromagnetic waves. And of course, there are many kinds of electromagnetic waves, including visible light, ultraviolet, X-ray, gamma ray, infrared, etc. Okay. And this is a picture of a sun emitting X-rays or X-ray, soft X-ray, or ultraviolet rays. Of course, this radiation cannot be seen with naked eyes, but you can use an instrument to record its presence. So the sun looks like this when it's under ultraviolet or X-rays. You also have matter waves. Quantum mechanics actually show you that when you go to a very small dimension, when you go to the atomic dimension or even smaller, you'll find that the particle, which the electron, the proton, and the neutron we commonly regard as particle, they also have the wave phenomena. Okay, so there's a term called wave-particle duality, which means that the elementary particle all have the property of a particle and also have properties of waves. They have 2 kinds of properties. So that's called duality. Duality means you have 2 sets of properties for those particles. Electron, neutron, they can undergo diffraction. Okay, if you have some electron impinges on a crystal, for example, the space between the lattice, the atomic lattice, you know that in a crystal, the atom are arranged in planes which are very regular. So there are gaps between this plane, and they act as scattering center to scatter the electron wave. So when you have electron impinging on the crystal, the outcoming electron will become scattered like waves. And this is a typical scattering pattern or diffraction pattern of the electron by the atoms in the crystal. So that shows that this phenomenon shows that the elementary particle indeed have wave properties, just like the ordinary mechanical waves. We have the transverse wave and longitudinal wave. If we shake a string, a taut string sideways, then the disturbance will be perpendicular to the direction of propagation, and that is a transverse waves. If you have an air column and you compress and rarefact the air column by using a piston, then those compression and rarefaction will propagate along the air column, and that is the longitudinal waves. In the longitudinal wave, the disturbance and the direction of propagation are in the same direction, while in the transverse waves, the disturbance and the direction of propagation are mutually perpendicular to each other. Okay. Now let's describe the wave kinematics. Let's now learn the language to describe waves. Now we actually confine ourselves to a simplest problem. We consider a taut string, a string that is pulled at both ends with a tension, such that it is taut. So we now consider a disturbance, a small disturbance on the taut string. So that is a transverse waves. Okay. Now, actually, for other waves, we can easily generalize the equation of motion to other cases. So we only confine ourselves to these cases. Now, how to describe that? We first look at the string. We want to label different parts of the string. So we use the label X, okay? X equal to 1, I refer to this part. X equal to 2, I refer to this part. X equal to 3, I refer to that part, and so on and so forth. So X is a label along the string. If I say I'm looking at X equal to 1 cm, I'm always looking at that part. Now, it's different from your previous notation. In your previous notation, in kinematics, you denote X, you use X to denote the position of a particle. And the position of particle may change with time, right? The position of particle is here at time 0 and there at time t equal to, say, t equal to 1 second. Okay, so X in that case depends on the time. It is a position that is time dependent. But now we use X in another manner, in another way. X is no longer the time dependent coordinate. It is just a label that shows different position along the string. So X equal to 1 always refer to this part, X equal to 2 always refer to this part, and so on and so forth. There's just a label along the string and nothing more. It's not a function of time. It's not a function of time. It only labels a particular part of the string. So how do we describe the vibration? If X is not the quantity that describes the vibration, what quantity describes vibration? I use the quantity U. Now, U is the disturbance. I draw a vertical arrow here, which means that U is the disturbance of the string from the equilibrium position. I assume the x-axis to be in the equilibrium position, and then at this part, this small part, is now at the distance U, okay, from the equilibrium position. So this is the disturbance at this part. Now you can immediately see that U may depend on X, because you see different parts of the string may have different disturbance because the wave maybe have a peak here and a trunk and another position. So U must be dependent on X, right? Is that right? And U must also be depending on T, because the whole wave will propagate forward. Okay, it will propagate forward. So at a certain point, which is a peak of the wave, at another time when the wave passes, at another time it may become a trunk. Okay, so the disturbance itself must also be a function of time. Okay, so that means the disturbance U of the waves is a function of both the label of the position X and also is also a function of time. It depends on both X and T. And X and T are independent of each other. Okay, X is just a position that you are looking at. Okay, and T is the time that you are looking at. They can be chosen independently of each other. You can look at the wave at this particular position at different time. You can also look at different part of the wave at the same time T. So they could be chosen independently. They are not depending on each other. X and T are independent variable now. So in short, if I write U as a function of X and T, U is the dependent variable, and X and T are independent variable. They can be chosen arbitrarily. You can choose where to look at the wave, and you can choose when to look at the wave. Okay, they can be taken independently, and U depends on both of them. Okay, and the warning is now when we talk about waves, X and T are independent. X is not a function of T anymore. Okay. Now we assume without proof that a wave with a single frequency can be described in this form. Okay, this is just our assumption. Now look at this formula. Now this is called a sinusoidal wave because it takes the form of a sine or cosine function. So we call it a sinusoidal wave. Now look at the form of this equation. Now, of course, in general, you may add a constant phase phi, but for simplicity, we omit this at the beginning. Now look at the structure of this equation. Now the coefficient that goes before the cosine is of course the amplitude, right? The amplitude of vibration. It denotes how large the vibration is, right? So I denote it by U0. Inside the cosine, you have both X dependent and T dependent. You have Kx minus omega T, where K and omega are two constant. The constant K is called the wave number. The constant omega is called the angular frequency. Now the angular frequency is just the same constant you see before when we discuss about circular motion or simple harmonic oscillation. It is the same angular frequency, but you have now another constant which we call K. Now K is called a wave number. Actually, is related to the wavelength. Okay, we will see later. Okay. Now, and this combination Kx minus omega T, we call it the phase. Okay. Now let's take a snapshot of the wave at t equal to 0. Assume that t is equal to 0, so we don't have this term. Why we call it a snapshot? Because when we set t equal to 0, that means we are looking at the wave at a particular time. That particular time is the starting time. So effectively, we take a snapshot of the shape of the wave at the beginning of time. Okay. So that means we freeze the time. We're looking at the wave at time 0. Okay. So that's why we call it a snapshot. It's just like using a camera, pressing on a shutter to take the shape, take a photo of the shape of the wave at a particular time. Now, so this is a graph, the snapshot at time 0. Now, when I put t equal to 0 here, the term omega does not appear now. So the wave at time 0 is u naught cosine kx, which is simply a cosine curve, right? The cosine curve looks like this, okay? With maximum value equal to u naught at x equal to 0. And it's repeating itself with a wavelength lambda, okay? Now we can find out what is k. We can find the relation between k and lambda. Because the wave repeats itself in a length equal to the wavelength, which is lambda, the wavelength is lambda. And that means when x goes from change from 0 to lambda, the cosine function will change for 2 pi, right? The argument in the cosine will change by 2 pi. Because 2 pi is the period of the cosine function. So if you go for wavelength, if you go forward for wavelength, which is lambda, if x increase by a wavelength, then the phase factor kx must change by an angle 2 pi. That is equivalent to a complete period. So that means k lambda is equal to 2 pi. And here becomes the relation between k and lambda. So k, which is called the wave number, is just 2 pi over lambda. Now this is actually very similar to the expression between the relationship between omega and the period t, which we will discuss below. Now then, we consider a motion in a specific part. What's the meaning of that? We look at the particular point on the wave at different times, okay? So for example, we look at the position x equal to 0. We look at that particular position, but we plot the disturbance u against the time t at x equal to 0 for different time t, okay? And see how u vary with time. Now, if you put x equal to 0 here, then you don't only have the cosine omega t term, right? So it looks like something like this. So u is just u naught cosine omega naught t. So if you plot u against the time t, you got a cosine curve also. But be careful. Now the independent variable is t, but not x. In the first graph, we have a snapshot. This is the real wave. So we plot u against x, the waveform that gives you the waveform at time 0. But now this meaning is different. Now we look at a particular point on the wave that is x equal to 0, and we see that point going up and down. Okay, so we can plot the disturbance of that point against the time t, and that is again a cosine function. So the cosine function goes like this. When the cosine function repeats at the period time t, this is a period. It goes back to the maximum. Okay. So again, if I consider a period, if I consider advancing a period forward, when t change by a period t, then the phase inside the cosine must change by 2 pi. And that's give the relationship between the angular frequency and the period. Omega is 2 pi over t. Now, we actually have seen this a few times before. When we talk about circular motion or when we talk about oscillation, we still have this relation, okay? And you can also see that when we are looking at a particular point on the waves, the particle there undergoes a simple harmonic oscillation. Because the particle, for example, the position at time at x equal to 0 is a cosine function, which means that point vibrates up and down. If you look at still another point, if you take a look at this formula, if you look at another x position, for example, x naught, then apart from this constant phase, the particle still exhibit a simple harmonic motion. But there's a phase difference between the particle x and a particle at x equal to 0. They may vibrate at different phase, but they vibrate both in a simple harmonic motion. Okay, so what is called wave is just a accumulation of a lot of simple harmonic oscillator. You can imagine now along the x direction, there are a lot of simple harmonic oscillator, and each simple harmonic oscillates in its own phase, but with the same frequency. And the superposition of all these simple harmonic oscillator will result in a wave pattern that propagate forward in space. That is called waves. Okay. Now then we proceed to find the wave, the speed of the waves. Now this is a graph of u versus x, which is a snapshot. Okay, we take the snapshot of the wave at time 0, and then we take the snapshot of the wave at another time, which I call t. So during this time, the wave actually has propagated forward by some distance, and I call this distance x. Now this distance denotes the distance that the wave propagates in the time t. Do you understand? Okay. Now we look at this the formula now. The formula looks like u naught cosine kx minus omega t. Where is the peak of the waves? Where is the first peak? The first peak corresponding to this factor, when this factor is equal to 0. When kx minus omega t takes a 0 value, the cosine function is the maximum. So that corresponding to the first peak. Okay. Now, when t is 0, it's simply kx, right? And so x equal to 0 correspond to this peak, which is denoted by a dot, the red dot. But when t is larger than 0, for general time t, the peak is no longer at the position x equals 0 because it's moved forward. And the position of the peak is just given by the x such that the combination kx minus omega t is equal to 0. So this position actually corresponds to the point where the combination kx minus omega t is equal to 0. So in doing so, we actually follow the waves. We follow the first peak of the waves. At time t, the peak is here. At time t equal to 0, the peak is here. At a general time t, the peak is here. Okay. The wave speed is just the distance traveled by the wave, or equivalent to the peak per unit time. So at time t, the position of the peak is x, such that kx minus omega t is equal to 0. And so I can find x over t. X over t becomes the wave speed. I denote it by the parameter v. So the wave speed v is x over t. And from this equation, we find that the x over t is just omega over k. So that means I can express the velocity v of the wave in terms of omega and k. Now, but it is very obvious. Actually, you can understand why the wave speed is so by using your high school physics. Well, we have learned that omega is 2 pi over t, while the wave number k is 2 pi over lambda, right? So that means omega over k is nothing but lambda over t. Lambda is a wavelength, t is the period. The wavelength is just the distance traveled by the wave in one period. So the wavelength divided by the period is nothing but the velocity of the waves. And in your high school study, you commonly denote 1 over period as the frequency. So the frequency multiplied by the wavelength lambda will give you the wave speed. That is the equation you learned in high school. Now we obtain the same thing. The only difference is that we now know how to express the wave speed in terms of the constant omega and k. Omega is angular frequency, k is the wave number. But that is not different from the high school formula. Okay. Now there are other peaks along the waves. For example, if you put an integer n here and you set kx minus omega t equal to n times 2 pi, or n is an integer or 0, then you simply are following different peaks along the waves. Okay. For example, if n equal to 1, then you're probably referring to this peak. If you n equal to 2, then it would be referring to the second peak, which is somewhere here. If n is equal to -1, then you go to the negative side. You follow the peak there. Okay. Now here we have a classwork. Okay. The classwork is give you a formula of a sinusoidal wave, and you have this constant. You are required to find the amplitude, wavelength, period, and the speed of the waves. Now, this actually is quite easy. I just want you to get familiar with the physical quantity that are involved in describing the waves. So when you compare this with the formula, with the standard formula, U equal to U naught cosine kx minus omega t. This is the standard formula. Then you find that this guy is actually the amplitude U naught. And this guy, this constant that goes before the x is the wave number k, right? And this number that goes before the goes before the t is the angular velocity omega, or the angular frequency omega. Okay. So with omega k and u naught, you can calculate the wavelength. The wavelength is what? The wavelength is just related to the constant k by this formula. K is 2 pi over lambda, so you just make lambda subject. And the period t is just related to the frequency omega by 2 pi over omega. Okay, so after you just substitute these two values into the equation, you get lambda and t. And you can also calculate the wave speed by using this formula, lambda over t, since you know lambda and t now. And also, you can directly calculate the wave speed by using omega over k. The relation is V equal to omega over k. Okay. So I prefer not to spend extra time on the lesson doing it. So please try to do it at home and see if the value you find match this answer. Okay. Now let me stop here.